Hey, Business Cal students. So we're going to continue the conversation we started earlier. Now that we all have had a nice refresher on what a natural log is, or a logarithm in general, as well as the exponential function, we're going to discuss how to take the derivative of these functions. So we're going to start off with number one, the derivative of e to the x. Well, this is going to be e to the x, just like this. All right, we're going to show how this is the case. We're going to do kind of a bit of a roundabout proof because, a true proof would not involve us resorting to graphs. But I just want you to get to see kind of what's going on with this rather than go through every single step of the derivation. So let's go ahead and start with the proof before we get to here. We are going to use this, but let's go ahead and get this started down here. So we're trying to find the derivative of e to the x. And we're going to use the formula. All right, limit as h goes to 0 of e to the x plus h minus e to the x divided by h. And I want to say that I expect you to be able to reproduce this for any function, at least this first step. It's very important that you understand how this goes, because this is the heart of every single derivative that you will come across. Even if you don't see it, this is what's always running in the background. All right, so let's go ahead and we're going to break this up by factoring. Right, you notice we can, this guy right here, this is e to the x plus h. So we can factor out an e to the x, and there's an e to the x in both of these. So we're going to write limit as h goes to 0 of e to the x times e to the h minus 1 all over h. Right? All we did was we just factor out an e to the x here and an e to the x there. All right. So now let's look at this right here. We know this tells us that's going to be 1, but let's verify this by looking at a graph of it in Desmos. All right, so you can see that here on Desmos we have it graphed. We have e to the h minus 1 over h like we did before. We want to know what happens as h gets closer to 0. What happens as this guy approaches our 0. So we're going to zoom in, and you notice it is in fact approaching 1. Now what happens if I actually plug in h equals 0? It is undefined. If I can get it right on there, I think you can see it pop. There it is. Undefined. So right at that point, it is undefined. But what is it approaching? It's approaching 1. Okay, so, and you can verify that if you put 0 into here, e to 0 is 1. So you get 1 minus 1, 0 on top, 0 on the bottom. And so we can see that the way they both approach arrives us right here, right at 1. It's getting closer and closer to 1. All right, so let's go ahead and finish this guy off then. We can go ahead and come on down here. This is the limit. Well, we want to pull this e to the x out and write the limit as h approaches 0 of e to the h minus 1 over h. And so we're taking the limit as we get close to 0. Again, if you were to evaluate it directly at this point, you would get an undefined, but we can look at what's going on as we get closer to 0, and that is it's approaching 1. And so that means that this is simply e to the x, just as we claimed earlier. So let's go ahead and work the following problems with this in mind. We want to take the derivative of this guy here, f prime, and I would say at this point press the pause button and try and work the derivative for each of these and see if your work matches my work. This is the best way to figure out if you have any gaps in your understanding or if you're doing well. All right, so we're taking the derivative here. Now this is the derivative of 2ex with respect to x. Now note this 2 is a constant, so it can come out. So it's going to become 2 times the derivative with respect to x of e to the x, which we know is simply e to the x. Right, so it's its own derivative. As it turns out, the e to the x is the only function whose derivative is its own derivative. It's kind of an incredible thing to think about when you start to contemplate. You know, when you say it's its own derivative, it means that every point you evaluate the function, that is its own rate of change. And so you can kind of see the way it accelerates upward so much when you look at the graph. That's part of the reason. As you increase, the rate of change is increasing as you increase with the function. All right, let's look at this one. You know, we're going to take f prime of x, and so it's derivative with respect to x of 2ex minus 8. And we can break this up. The derivative with respect to x of 2ex minus the derivative with respect to x of 8. Now 8 is just a constant, so its derivative is 0. And so this next one, 2e to the, well, we've already done that over here. We already know what it is. It's just 2 times e raised to the x. So it's interesting. You can add whatever constant you want onto here, and your answer is still going to be the same. It can be an 8, it can be a 2, anything. This will become an important tidbit as we get into integrals. All right, now for this one right here, f prime of x, the derivative with respect to x of 5ex plus 1/2 x squared. Again, we break it up. 5e to the x is going to be simply its own thing. And so here we have plus on the second one, plus 1/2 2x, right? We just use the power rule on this one. And you can see 1/2 times 2 just go away. And so what are we left with but 5ex plus x? And there's our answer for that one right there. All right, so now we're going to go on, and we're going to find the second one. Don't know why the mark's there. All right, we're going to find the second one over here, the natural log of x, and I'm going to go ahead and tell you right off the bat that the answer is going to be 1 divided by x. And we're going to go through the derivative, the proof of the derivative, but first, before we get too deep into it, we're going to look at a graph again, because I want to make sure you're understanding what's going on, at least at from a high altitude position, rather than getting too deep into the nitty-gritty. So, but we're going to start by saying, okay, what is the derivative with respect to x of the natural log of x? And so we start off with the proof, or I'm sorry, the definition, which is the natural log of x plus h minus the natural log of x. And this will be all divided by h. All right, so you can see I've graphed the limit that we're looking at right here. And I've also graphed what I've proposed is the derivative of the natural log of x, 1 over x. And for h, I've placed a slider here going from 0 to 1. And we're going to see what happens to this function as h gets closer and closer to 0. And so you can see it's approaching, and then when we finally get really close, you can see it's almost right on top. You know, it disappears at 0 because technically, you know, it's going to be a 0 divided by 0 error. So we're trying to see what's happening as we get closer and closer. So I'm going to go ahead and get really close in. You can see it's the closer we get, the closer h gets to 0, the closer this guy right here approaches this guy right here. Now you may notice that, you know, our function is not defined on this side. And that's because we can't take the natural log of a negative number. Now what if we're looking for the natural log of the absolute value of x? When we do that, go ahead and change this real fast. And just a reminder, the absolute value takes a negative number and makes it positive. It starts to come on across. I think I might hit the wrong button on here. Let me see. Okay, yeah, there it is. For some reason, Desmos really wants a parentheses around it, so that's what we have. But you can see that if we're taking the derivative of the natural log of the absolute value of x, well then 1 over x covers the whole gambit. So there you go. So that was the mile high view, the high altitude view. Now we're going to get a little bit into the thick of things, but before we do that, let's go back up to here. Natural log equals 1 over x. Also, we're just going to put this on the side. The derivative with respect to x of the natural log of the absolute value of x is 1 over x as well. Just to kind of cover both bases there. This one over here, of course, would only be valid for certain variables that are positive, I mean. Okay. So we looked at the mile high view. Let's zoom down and let's kind of work through the math to see why this is the case. Let's look at the gears and figure out exactly what's going on. And while we're working with this, I want you to keep this definition in mind. E, we talked about E, it's 2.718, and it's got a non-repeating infinite amount of decimal places. But one of the ways we can define, and there are multiple ways to define E, but this is kind of the more traditional way to define E, is to we use a limit, we say as m approaches 0, of 1 plus m, and then raised to the m. All right, this is one definition. There are other definitions that are very similar to this. There are some that are not so similar to this form, but this is the one that I want us to keep in mind for right now. So let's go ahead and keep moving forward with this guy. We're going to go ahead and combine these two functions, expressions there, because you may recall that the natural log of A minus the natural log of B is going to equal the natural log of A divided by B. That's a property of the logs. If you don't have this committed to memory now, I very strongly suggest you commit this expression to memory. It is very useful. All right, so we're going to go ahead and use that one. So we're going to say the limit as h goes to 0 of the natural log of x plus h divided by x. And this is all, well, I could put it over h. We're going to write it over here, 1 over h. Just to kind of capture that value there. Now there is one other property that I hope that is not unfamiliar to you for the log or for logs. I'm using natural log, but it applies for any a log of any base. But if I have the natural log of some letter times this, well, it's going to be, I can rewrite this as the natural log of m raised to the m. Right? This exponent can come up to there. All right, and that's what we're going to use right now. We're going to say the limit as h goes to 0 of the natural log of x plus h divided by x raised to the 1 over h. And we're going to go ahead and, you know what, let's go ahead and distribute this x down here. So we have 1 plus h divided by x. Now, to move forward, we're going to have to do something that's very clever. We're going to have to create a definition just for this proof before moving forward, because one of the things that we want to do is we want to make sure we're utilizing this. This is very helpful. It's not for no reason that I wrote this here. Note that this guy here, you know, it's already bearing some resemblance to this guy here. We want to make them look very similar. You know, we want to be able to bring the limit inside the natural log so that we can reduce it. So one of the things we see is we've got an m right here, and then we've got an h over x. So we're going to create a definition that allows us to substitute that h over x to m. So we're going to go ahead, I'm going to write this in, yeah, I'll do it in this pencil. So we're going to say let h divided by x equal m. Right, so that way we can replace this h over x with that m. Now note we can rewrite this expression so that we have 1 over h equals m divided by x. And so that is going to take care of this guy right there. So we're going to make those substitutions. Third and last thing we want to note this h approaching 0. Well, what's m going to do? What is m going to do as h approaches 0? Well, x is a variable, but if h is approaching 0, 0 divided by any number is going to be 0. So this means that m will also approach 0 as h approaches 0. Zoom in so I can write in as h approaches 0. So we can do these things. Alright, so let's go ahead and write this all down. The limit as m approaches 0. And you know, I'm going to go ahead and stick with that color code so that way it's abundantly clear. As m approaches 0 of 1 plus m raised to the m over x. Now, oh, and I forgot to write the natural log. Sorry about that. That is very important. There we go. ln natural log. All right, so we're going to use this property again to pull out this x right here so that we've got equals the limit as m approaches 0 of 1 divided by x times the natural log of 1 plus m raised to the m. And so now I can, since this 1 over x is not impacted, I can pull this out of the limit. And also the limit itself, we can bring this inside of the natural log so that we get the limit, 1 over x times the natural log of the limit as m approaches 0 of 1 plus m raised to the m. And so let me go ahead and highlight this for you. You look at this right here, notice it is exactly the same as this right here, so we can call it e. And so we have equals 1 over x times the natural log of e. The natural log of e is just 1, so it becomes 1 over x. And note that if I'd used, if we were looking for the natural log of the absolute value of x, it would have worked out exactly the same. Okay, so that's the nitty-gritty proof. We started off kind of looking at the graph to kind of verify that's what we were, that was in fact the derivative, 1 over x is. But this is the actual proof, the rigorous proof that is working behind the scenes. All right, so let's go ahead and work some examples now that we're armed with this knowledge. All right, so we're going to take the derivative. First, we take the derivative of that guy. Well, that's just 3e to the x. And now we're going to take the derivative of this guy. Well, that's going to be 5 times 1 over x, so just 5 over x. So note the derivative is undefined when x equals 0, but for everywhere else, it's fine. Okay. All right, so this next one, f prime of x. Derivative of the natural log of x is simply 1 over x. And note that this is only valid when x is greater than 0 because there are no absolute value signs there. Okay, plus 32 times x, 31. So remember the 32 comes out in front, and then we reduce the 32 by 1. And then e to the x is just e to the x. There you are. So you can see how these theorems make our lives really easy. I mean, imagine using the formal definition every single time we have to calculate one of these guys. All right, so the last one here is simply f prime of x equals 2ex plus, you know what, I'm going to go ahead and restate this one because you might not see what's going on here. So 2e to the x plus 10 times x to the negative 1 exponent, right? That's what this means. And so now we just use the power rule of 2, sorry, let's go ahead and write f prime of x now. 2ex, and now we're going to say, all right, so the negative 1 comes out in front, so it becomes negative 10 times x. And what is negative 1 minus 1? It is negative 2. And that is our answer. Okay, good. All right, so we've got one last set of theorems to work with. For these, I'm just going to go ahead and state them rather than work our way through the proof. So this one is going to be natural log of b times b to the x. And then this guy over here is going to be, 1 over x as it normally would, but you're going to multiply it by the natural log of b, whatever that base is. And so let's just I'll give you a few quick and dirty examples down here. So if we say one of the derivative of 10 raised to the x, well, that's going to be the natural log of 10 times 10 raised to the x. And so over here, let's say we take the derivative of just log of x. Remember, that would be log base 10. This is a common log, so it's probably one that you'll have to do frequently when you're going through other coursework as well as career-wise. And this would be 1 over x times the natural log of 10. And that's it. That's how we work these. So like I said, other than the natural log or e, 10 is probably the most common number you'll be using, but keep in mind this applies across the board for any base that you're working with as well. Also note that if b happened to say b equals e, well then you would be taking the natural log of e, which is just 1, and so then it'd simply become e to the x as it normally is. Okay, with that being said, let's go ahead and move forward and finish everything off with this nice example right here. Alright, so in here we've got an internet store that sells Australian wool blankets. If the store sells X blankets at a price of P per blanket, then the price demand equation is given right here. And so we're going to, for this equation, for this question, we want to know, okay, how does the price change as we increase or decrease the amount of blankets that we're selling? So we're going to find this by saying, okay, well, what is, and this is called the marginal price. This is one way of finding things. So we're going to say, okay, what is dP dx, right? How does the change of price change with the, as we increase or decrease the number of blankets for sale? And so we just take the derivative here. So this is going to be 350 times 0.999x, and note that this 0.999, that's our v value. So we got to take the natural log of 0.999, and there we are. That's it. That's how the price changes as we vary things. All right, so that was a pretty simple operation to work with. I encourage you to graph this equation in Desmos just so we can kind of get a feel for how things are going. That is all we have for today, so I will talk to you guys tomorrow.